All right, line P5, learning task 1. We have now moved out of our low voltage transformers and we have gone into high voltage transformers. And once again, we just need to iterate where our breakdown line is for low to high voltage. For us as electricians, anytime that we pass over 750 volts, according to the Canadian Electrical Code, we have then moved into the high voltage range. So these are all going to be things that are placed over the 750 volts. In a lot of cases, the things that we're going to be looking at inside of these next couple of learning tasks are actually going to be higher, more towards the 25,000 and higher type of range that we're commonly going to see a lot of these connections here. Learning task 1 goes through a lot of the construction and the features of high voltage transformers, and for the most part they're going to be fairly similar in what the purpose is. The purpose of transformers is generally to go and change our values of voltage and current. We'd like to bump up our value of voltage, which drops our value of current, so we can increase our transmission distance while not having as much of losses on the system, I squared R losses, nor as much volt drop on the system, IR drop. So we like to go and take from our medium values of voltage, we're going to increase them to really high values of voltage, transmit them across the province, and then we go and drop them back down again. The first little bit out of our learning task scope here goes through core construction, and early transformers were created around, they need to have something magnetic to carry those flux lines that were created around solid iron cores, but there was a lot of problems with that. We had a lot of eddy current losses that would go and happen inside of these. So if you take a look at this block that we have, if we have current, we're going to go and have eddy currents. We're actually able to go and have eddy currents that are going to go and circulate in all sorts of different directions. If you take a look at it as 3D, you can see it circulating on all three faces. To go and reduce that, eventually they went to using stranding, similar to having cable or wire rope that they would go and have. And then they went from there to the laminated steel cores that we are going to go and see today. Generally speaking, our laminated cores are going to be made up of silicon steel. The silicon steel is going to be a very high electrical amount of resistance, and because the resistance is going to go and be so high, it is going to go and make smaller values of eddy current. And the laminations, which are insulated by layers of insulation in between, so we'll varnish in between each of these layers here, are going to go and break down your eddy currents, so your eddy currents are not able to go and form as big. They get broken up by those lines of insulation. Smaller eddy current pathways means that we're going to go and have less losses as well. So we're going to go and lower the amount of total power that we're going to dissipate off of the transformer. Transformers put out heat. If you've ever been by an active working transformer, you know that those things go and place out a fair bit of heat. So the less that we can go and take off the actual transformer itself, the more efficient it's going to be, because ultimately we're looking to transform voltage and current to send it out to a load, not to go and heat the actual transformer winding itself. We do have silicon steel as well because it's also going to go and have a high permeability. And permeability is just the ability for flux to flow. The higher the permeability, the more flux that we can fit inside of any sort of a given type of object. And we want to go and maintain as much flux as we can inside of the transformer core, because that means that it's going to then be aligned right next to my transformer windings, which means that we are going to go and cut through more windings. We're going to have, once again, more efficient transformation. As far as core construction goes these days, cores are going to be made up of multiple laminated layers. Those multiple laminated layers, the more layers that they can place into these, the better the construction of that transformer. But at the same time, you are going to go and have an increased amount of cost that's going to go along with that for you to slice that steel into smaller pieces and laminate them all together as well. As far as the windings go, the windings are going to be placed around oftentimes a bobbin or a spool, and then they're going to be placed into the actual transformer core. If you take a look at the transformer core, it's going to look something like this. I'll just draw out a set of windings. Windings are going to be made around spools. So they're going to make these windings just separately as spools, and then what they do is they go and take a core. I'm only showing two legs over here, not the third, but they take a core, and the core is going to be made up of plates that look like this, and if it was a three-phase core, there'd be another one further down over here, and then they're going to go and have another set that is going to go and overlap that's going to go and look the same on the opposite side. Let's draw this one out over here, and over here. So they make these windings just off of a plastic spool. They're going to bend them, insulate them, etc. And then all they do is they go and take these two sets of laminations and they're going to go and press fit them together. You're going to see, if you take a look at the side view of a transformer, that the side view of the transformer, and I'll just make one that's made up of relatively few laminations. Just slice this one a second. If this were my transformer side view, you're going to go and see that there's going to be laminations that are oftentimes going to be overlapped like this. And that means that as they pull this thing apart, then they would be able to go and pull those two sets of laminations apart. You're also usually going to go and see weld marks. That means that they have welded in a rod or something like that through here to hold these ones together. So if I were to highlight one section of my transformer, this would be one section of my transformer like that. And it would be interlocked with another section of my transformer like that. And once again, we're looking at this thing from a side type of view. This would be the yellow section, and this one would be the blue section for how they're laminated together. They just wedge these or slide these two pieces together, and they make sure that they've got these spools of windings that are already pre-wound, and they're just going to slide these two cores together into the center of those two. For low power, low voltage transformers, usually it's going to be a relatively thin amount of insulation that we're going to place around the windings. It's going to be varnish or enamel, which is going to be an oil-based type of paint, basically, that goes on there. Now, varnishes and enamels do, over time, they can go and degas, where they're going to go and lose their VOCs, or volatile organic compounds, which are the things that make oily things oily, for lack of a better, more sciencey term for that. As soon as that starts to happen, there will start to be insulation breakdown. So the varnish will break down over the years because it's ever so slowly just releasing those VOCs. This is why transformers need to be taken in for periodic service and electric motors as well. The rewinding and revarnishing is there just to go and put a new coating over top of that. If we go into higher voltage, we're going to go and have a stronger type of insulation between the windings. They call it a dielectric in a lot of cases because they don't want us to think about it as being insulation that prevents current flow. They want us to think about it as being something that is going to be affected by the current flow. So they'll call it dielectric. It's the same thing. And they're oftentimes going to go and use oil impregnated paper. So they're going to go and take paper, they're going to wrap it around. The paper forms a physical barrier, then they vacuum in the oil. And when they vacuum in the oil, then it is going to go and fill all the pores of the paper and give you a really good insulation in between. If they want even better type of transformer winding encapsulation, they're going to go and take your entire transformer and they're going to go and vacuum out the inside. So it'll be inside of a sealed canister. They're going to stick the low end into epoxy. They're going to attach a massive vacuum pump to the other side. And they're going to pull the epoxy all the way through. This removes all air bubbles so we don't deal with problems like corona and things like that that are going to be inside of there. And it's also going to go and fill it up with that epoxy, which is then able to go and harden. Ultimately, the leads of the transformer do need to be connected to something that's going to take them external. This is going to be called the taps, or the places where we are going to go and make our connections. In high voltage, a lot of times the taps are going to be connected to something that's automatically going to be able to go and change the values of transformation. Those are going to be referred to as being our tap changers. They do have components of an oil-filled high voltage transformer. There's a diagram that's coming up over here, and we do have a set of tap changers. Now, first thing, before we go to this diagram, we're going to go back and forth to this diagram here, is just we need to go and note that the numbering was done wrong for that table. What you should do is you should number the way that I have it here. What they did inside of the book over here is they went, 1, 2, 3, 4, 5, 6. Really, it should be 1 through 11 down there, and then 12 through 21 down the other side. Renumber your book like that so that you can actually follow along with what's happening inside of the transformers here. All right, I'm going to go back to my bigger picture of the transformer over here. Tap changers are often going to be seen as a circular type of object because circular objects are going to allow us to kind of rotate through from one point to another. In second year, you should have seen some cutaway diagrams of tap changers. You might need to refer back to that. This is just going to be the same thing, but it's going to be covering 3 separate tap changes over here. And it's going to go and have our windings, which are carried from the inside of our transformer over here, are going to get carried out to these taps. This is going to be a rotary set of brushes that are going to go and make and break these, sometimes with small reactors that are attached to it, and then that rotary set of brushes taken outside, coupled through mechanical shafts down to a motor that is then going to be able to be used to change these taps. We don't obviously want to go and send linesmen into these to change the taps. First of all, changing taps is a bit dangerous because there is always potential for failure. And secondly, we want to be able to do this thing remotely from wherever we've got our control yard for these. Cooling methods for high voltage transformers. Obviously, we want to keep these things relatively safe because if we allow high voltage transformer to go and overheat, we end up with catastrophic failure. Low voltage, the failures can be bad, but high voltage failures are often much worse. You can just go through YouTube and look at high voltage failures. You just see the extent of damage that happens within milliseconds. There's an equation, we talk about this often, they call it the Arrhenius, I don't know how you pronounce that, Arrhenius equation, but it basically says that your life expectancy for electrical insulation is going to cut in half for every 10 degrees increase in operating temperature. Generally speaking, as a rule of thumb. Over top of 30 degrees is usually where we start that, so about 30 is where we stop it, so if you go 30 to 40, you're going to get about 50% less life. 40 to 50, you're going to get 50% less of that 50% less. So you're going to be down to about 25% life, etc. So the more heat that we allow to go and be maintained on an object, the greater the chance of failure. Because of this, we're going to try to go and cool our transformers as effectively as possible. If it's a smaller size, we're often going to go and cool them through air circulation. It's just going to be air that's going to be allowed to go over top of the windings. But the problem with air over top of high voltage windings is that air is often going to go and have moisture that's going to be associated with it as well. And air itself is not super dense, so it's not able to always go and carry it away. Other times we're going to go and have forced air that we're going to go and place through fan force. It's going to be thermostatically controlled cooling fans. As it gets hotter inside there, we're going to go and push more air through. But ultimately, what we mostly are going to go and see is we are going to go and see a filling made up of some sort of a liquid. You'd all know this, that if you have got air and water, where does the water sit? Well, the water is going to go and sit in the bottom of a container. You just mix it up, take a water bottle, shake it, and you'll see that the water all sinks to the bottom. This tells you that the water is denser, and because it's denser, it is going to be more effective at carrying out heat. Same thing with oil. If you had a container full of oil and air, if you shook it, the oil would sit to the bottom. So the oil is going to be denser, which means it's going to carry heat away more effectively. And so what we're going to have inside of a transformer is we're going to go and have a sealed can that is going to be filled with oil or other types of liquids that are going to be inside. And it's going to be similar to the setup that you have inside of your vehicle radiator. For those of you that turn wrenches on your own vehicles, you know that you're going to go and have the entire system over here that's going to be filled with oil, and then there's also going to be a reservoir up top over here, and the reservoir is going to go and have a bleed valve on it and everything like that, because what the reservoir is going to allow us to do is as we heat this thing up, so as my heat goes and increases, the mass, the volume of my cooling medium is going to go and expand. Heat up water, heat up oil, you're always going to see this thing expand, which means it's going to go and push up into here, so it's going to go and bleed a little bit of air out to the outside. As it cools down, it is going to go and drop its volume, which means that it is going to go and pull back down into our transformer over here, and we're going to allow a little bit of air that's going to go back into the top of this tank over here. We don't want the air inside of the transformer. We want to keep all of the air inside of the tank, any little bits of air that we're going to go and have back and forth. Usually, it's going to be some sort of a mineral oil that we would use in a lot of our older ones. They would go and treat it, which means that they're going to go and place in a couple of other chemicals to go and keep it from cooking off like a bomb. You've got oil, you've got electricity that burns at 3,000 degrees, and basically you've got the making of very large bombs. So they would go and place in chemicals. One of the most common chemicals that you will have heard about is going to go and be my polychlorinated biphenyls, or PCBs. You're going to hear this off of a lot of stuff. Old transformers have it, old lighting ballasts have it. Pretty much anything that is old and has oil or tar in it is going to go and have PCBs. And these are highly regulated because they are so toxic, cancer-causing, carcinogenic, environmentally toxic, poisonous, etc. They would go and treat the oil. They wouldn't have to place a lot, but they would place just enough in it to go and prevent this thing from cooking off. It really just raises the flash point of the oil, so you have to get it way hotter before it's going to be able to go and catch fire. Nowadays, they're moving away from it because PCBs are so highly regulated. They're looking for other cheaper methods to go and use. And so we are going to often use other gases inside of there. One of them is going to be nitrogen gas. Nitrogen gas is the same thing that we fill, a lot of our inert stuff. Optics are filled with nitrogen gas. Light bulbs are going to be filled with nitrogen gas. It's just going to be an inert gas. It is not greatly effective as far as an insulation is, but it's better than air by itself. It's going to be, because we've evacuated and put in the nitrogen, we're not going to have any moisture or anything that's going to be associated with it as well. So we'll use it kind of in our medium voltage range. When we get to really high values of voltage, we're going to go and see sulfur hexafluoride Sf6. And Sf6 is kind of a cool gas. Yeah, look up YouTube's on Sf6. You can huff Sf6, it's not good for you, but it does the opposite thing as helium. Instead of your voice going all high and cracky, it's going to go and get, really low. You can go and place stuff inside of Sf6. You're still able to go and breathe inside of Sf6, but Sf6 does have really good insulation properties, but it is also highly regulated. Out here in North America, we still cowboy it up. We don't really regulate it as high as the European Union does, but the European Union does, because small amounts of Sf6 are equal to massive amounts of carbon dioxide when it comes to the amount of insulating properties, not just electrical insulating, but thermally insulating. So if you have escapes, if you would lose a transformer full of Sf6, in the European Union, you would be facing massive fines, because it's equivalent to, for every liter that you would go and lose, it's equivalent to losing, I think it was, and don't quote me, I'd have to look this number up, but it's a couple thousand liters of CO2, or a couple 100,000. It's a massive amount. So they go and highly regulated out there as well. Maybe this is going to be something that, in our lifetime, we're going to talk about how we used to use Sf6, and then we found out it was so dangerous, and now we don't use it anymore. But at this point, it is still commonly put into use. As far as our transformer diagram is concerned, transformer diagram is going to go and show a couple of main things. You can see the tank and the lid, and the conservator tank, which is where we're going to go and hold, a bunch of our stuff. They've got the buckles relay, which is basically going to be something over here that is going to go and detect gas bubbles. Anytime that there's a bubble that goes through here, it is able to go and send us an alarm signal, because gas bubbles would mean that we have got usually arcing inside of there. Tap changer is going to be this assembly over here. Tap changer is going to be coupled to an external motor through a drive shaft over there. That is going to allow us to change those taps as we go through. And then our high voltage bushings are going to go and be these things over here. And we know it's going to be high voltage because they're really tall, and they've got a lot of these little fin sort of things around the outside. We're going to discuss those in a minute. That's going to be my high voltage bushing for my actual lines that are going to be coming in. I'm also going to go and have some smaller high voltage bushings that I'm going to go and use for a couple of internal components. One of those internal components is going to go and be my CTs and my PTs that I'm going to go and have. I'm going to go and take off some lines for my CTs and my PTs, because I don't want to actually have to access everything inside. We talked about metering in the previous video in P3. Now we're into our high voltage, and obviously we want to try and stay away from these high voltage lines as much as possible, so the manufacturers are already going to go and put in connections for our CTs and our PTs. The core and the core yokes and limbs are going to go and be the main area that we're going to wrap our windings around. If you go and take a look at your core that they go and place inside of here, you can see that that core is going to be a three-legged core, and then we are going to go and wrap our actual coils around it. They're just showing the coils over here like that. Last of all, I've got two sets of valves that I'm going to go and use. The two sets of valves are going to be used for filling the tank. I've got an oil release valve down here. I just lost track of where I was there. Oil release valve, and I've got a vacuum valve up top over here. And what they're going to do when they're filling this thing with oil is they're going to go and take a massive tank of oil that's going to be off to the side over here. They're going to fill this tank with oil, and then they're going to go and couple a line directly across from this tank through to here. And then what they're going to do is they're going to hook up a massive vacuum cleaner. Well, it's not a vacuum cleaner, but it's a massive vacuum pump on this side. And what they're going to do is they're going to go and suck out the air. And as they pull out the air, that oil is then going to go and flow in, and it's going to completely fill this transformer. And they're going to go until they get oil coming through here, because once they've got oil coming through there, they know that they have evacuated out all the rest of the air. They're going to fill this then with the remaining amount of oil up top over here, or whatever they're ending up using for their stuff. And then when they open up there's going to be a little valve inside of here as well. They're guaranteed that this entire thing is going to be filled all the way with whatever cooling medium they're looking for. All right, that's it for basic construction off of these. Once again, read through the module. There's a bit more detail that they go into on some of these, but our basic construction is that we need effective cooling, often done through other mediums, and we have got a completely different construction that is going to go and have pretty much everything on board. Tap changers, CTs, PTs, bushings, etc.